my presentation. I'm working currently for a company called Deepfield. Deepfield is in the network monitoring industry and specialized on monitoring very large and very complex networks and helping customers to maintain new KPIs. We will see soon what exactly this is about. We've chosen a little bit, let's say, aggressive title for the presentation. So slow is the new down. So network operators, of course, don't like both of these terms, to be slow or even down. Indeed, it's more about how to measure quality of experience in large networks. So what does really slow mean? Today we have a lot of services which we could tell they even don't work at all if they are delivered too slow to the end customers. And that means that slow isn't really much different from down. How do we detect slowness in large carrier and ISP networks? There is a part in the industry, in the over-the-top traffic industry, that is already monitoring their services. This is the service providers themselves. Like, for example, Netflix. Netflix is monitoring the service they are delivering to the end customers because they can do it because they maintain the server side of their service and the client side of their service as well, and then can use this connection to get performance data about how their movies and video streams are, how good they are delivered to the customers. Google is doing something like that as well, the video quality report. And the industry more or less agreed on a unit which is called average bitrate per stream. This is a new key performance indicator to identify if streams are delivered properly to the end customers. Cable labs is another part of the industry which is helping mainly US cable operators to maintain their network and to look into their performance data. So US cable operators are using Deepfield technology. A small part of our product was the video streaming score part, which allows us to monitor average bitrate per stream data in large networks. And these large networks share this information on cable labs to compare themselves to others. So many network operators ask themselves, okay, do I deliver a good video streaming quality to my customers? Are others better? Why are they better, right? And what is still okay? Is 3 megabits, 3.5 megabits for an HD stream still okay? Or does the video quality drop down to SD? So these are things we are looking for with one part of our solution. So why does this really matter? Why is it so important? If there is not enough capacity available, over-the-top services will just stop working. Customers will just not use them anymore. Slow is not really an option for streaming video. If you have a 60-inch screen in your living room and you just get SD quality, you may not really enjoy it, right? So you stop using these services. Video streaming has something like soft real-time requirements. So there is a small buffering phase only for video on-demand services, of course. Live streaming events are, there is not really a huge possibility to buffer, because if you think about sporting events like watching football games or things like that, you want to see what's happening at the same time when anyone else using satellite TV or something like that sees what's going on in these games as well. Other things that are important to consider when looking at over-the-top traffic and video streaming traffic is how exactly is this traffic, this content reaching my network, and how is it then on my network transported down to the subscribers? And if there is a problem in my entire network or in a region of the network, then you want to know it as early as possible. Other things we have in today's networks are on-net caches. So many of you may have Google caches in the network where traffic is not coming from the Google AS directly. It's coming from a local cache in your network and delivered on a short path to these customers. You, of course, need to maintain these and look for the performance of these services as well. You want to know, are they really used? Is it effective to use them? Or do I need to change something? Are these caches in the correct location, or do I need to place them somewhere else? And for over-the-top traffic, of course, you could have direct peerings to service providers like Netflix, for example, or Amazon Prime, services like these. Often you find these or you can do private peerings with them directly, or you find these at internet exchanges as well. And another thing to consider when monitoring these services is if there is a CDN involved in delivering the service to the customer or providing the service. For example, Netflix is actually making use of two different kinds of CDNs. They are using their own CDN, OpenConnect, to deliver the streaming video, and they are using Akamai to deliver the small pieces like the catalog information and these kind of things, because their own CDN is optimized to deliver just huge chunks of traffic. So very often you have a dependency between different sites to have the entire service working. We will look into a different example later as well. So you need an understanding of the cyber supply chains, how we call it. So the problem is today's tools do not really provide sufficient information to maintain these KPIs network-wide. What are we talking about? Is the situation getting better or getting even more worse? So if we look into what's going to happen, currently we are mainly talking about SD and HD streams. Service operators just start to deliver UHD streams, 4K streams to customers as well. They are consuming even more traffic. But it's not enough to just separate SD, HD streams. You can have HD streams with significant different bit rates. If you look at voodoo.com, for example, they have an average bit rate per stream of nearly 10 megabits per second. Netflix, an example here, has an average bit rate of 3.7 megabits per second. Another thing is that this part can be changed immediately. And not only because of the network operators change something if they make more bandwidth available. So the bandwidth usage here is more or less controlled by the clients. So for example, the Netflix client or the Amazon Prime device used to receive the stream. It's supporting adaptive bitrate. So even for HD streams, there are different kinds of qualities underneath, and you see that services have different requirements to the network. What network operators ask themselves is, are we really providing the best quality to our customers overall in the entire country? And if not, where is the problem and what can we do about it? Today, 50 to 70% of all traffic is already video. An impact could look like this. So Netflix could not load data, retry. This is a screenshot from a part from one of our customers to, let's say, quantify the issue. How big is the issue if something like that happens? So in this case, it's just looking at Netflix traffic and at the total amount of streams. So there have been 760 roughly concurrent streams via one CMTS. And round about at prime time, this went down to 0. We asked the customer and said, okay, there was some maintenance. We couldn't move it to a later point in time, and we had to reboot the CMTS. But it was available 10 minutes later. So, what happened? Because the customers stayed away. So it should have been ramped up here again, but the customer stayed away for 4.5 hours. what happened is that all these customers continued to watch their series on Netflix, but via the mobile network. And what the service operators don't want is they want to have all these load on a different part of the network, right? People are at home, but using the mobile network to continue watching these. Another point is that the impact felt by the customers, of course, is larger because it's just more present in the living room if you have a really large screen and it just doesn't work. So you may be not really happy as a customer with your service provider or something like that happens. So what do we need to understand OTT services in the network? First of all, we need an understanding of how the network overall has changed during the past year. In this case, it's looking at something like a 10 years time frame. What has really changed dramatically is the usage of CDN. Today, 60% of all traffic towards subscribers is coming from a CDN. That wasn't the case in, let's say, 2005. 2005, much of traffic was transit traffic. Then we had some peering traffic, internet exchange traffic, and some caching, of course, with local caches. Another thing we know from our data is that today only 30 different sites. So a site is something like YouTube or Netflix or Amazon. Only 30 sites generate 60% of all user traffic. And the high-value content, so the Netflix traffic, video traffic, and these kind of things, is nearly all is delivered via CDNs. Maybe purpose-built CDNs like Netflix Open Connect or Google Global Cache. Transits mainly deliver other traffic today. Most of it is adult content. IXPs are in a little bit special situation because many of them are really the gaming provider's choice because they are very close to customers as well. And gaming content isn't really made for caching. So today networks are more or less looking like this. We have new CDNs and new large data centers in different kinds of the world, mainly in large cities. But today already, all these CDN operators start to support the second largest cities per country or per region as well, because they want to be as close as possible to the customer and put as less additional node on the backbone of the eyeball providers, for example. So being as close to the customer as possible. Another thing we need to consider when we look into over-the-top traffic is, are there special events at special points in time? Why does something happen? So here, this is GMT time, so it's 3 o'clock in the US, 3 o'clock in the morning. You see that Open Connect traffic has a lot of inbound traffic. This is due to cache fill updates. So in that case, Netflix had new content and they want to load it onto their caches prior it's being used. The other graph here is just showing new CDNs on the market. This is important to know across all the different CDNs you are connected to, because you may be able to choose the best point in time when you allow your CDN provider or the CDN provider connecting to you to pre-fill their caches. So it's probably not the best idea to say, okay, can I do this at the same time? Right? Because there is already a lot of load on the network. So how can we identify over-the-top streaming traffic, for example? Legacy tools today don't really help a lot. Because what they see from just NetFlow data, SNMP, and maybe BGP is that there is a lot of web traffic. So in this case, web or HTTP traffic was 60% of the overall traffic of this carrier. And HTTPS is still growing. It's dramatically growing. Most of the service providers try to encrypt as much traffic as possible, because for fraud protection and other kind of privacy issues. So we will have more and more HTTPS traffic in the future as well. But somewhere in here, let's say hidden or tunneled, we have our video streaming traffic. Our video streaming traffic has totally different requirements than just web traffic. Web traffic is this, or downloads. Who cares if a download takes 20 seconds or 25 seconds? Nobody really. But people really care if, let's say, the buffering phase for watching a video takes 3 minutes instead of 10 seconds, right? Or if the video quality gets down because of a lot of network traffic and utilization. So it's really important to get more knowledge about what's inside this HTTP chunk. So what's going on with 60% of my network traffic? DPI has really problems to answer these questions. I know that many service providers do DPI, but mainly for, let's say, 5 or 10% of their network. That doesn't really help to identify regions where you have problems with video quality, because you may just cover the wrong region with this 5 or 10%. And DPI has really problems looking into HTTPS traffic because, yeah, of course, it's encrypted. What we do, we are using our own data feed to identify streaming traffic. I will tell you later a bit more about how it works. But we can compare, for example, Netflix delivering, or how Netflix is delivering traffic, delivering video streams. And there are 2 lines. The blue line is web or HTTP tunneled traffic or transported traffic. The dotted line is the average bitrate. It's around about 3.7 megabits per second. So this is HD streams. And this is more or less a flat line. So that means that the video quality over time is constantly good. The other line here, which goes up and down, shows the amount of concurrent streams. So even if there are a lot of streams, concurrent streams, the quality is not going down. So if you have problems in your network, then the dotted line would go down when there are many concurrent streams. Then there is some overload in the network or something like that. The other thing which this graph is showing is HTTPS traffic. The HTTPS traffic has only an average bit rate of 1.5, roughly 1.5 megabits per second. And that's all SD streams. So at the moment, Netflix is able to encrypt SD streams, and they only encrypt SD streams currently, but they don't encrypt HD streams, because I guess it's using too much performance or costing too much performance. Another thing that we can do to monitor traffic, so we are measuring the average bitrate per stream and the number of subscribers, so the number of concurrent streams. We can do this for all kind of over-the-top service providers like Netflix, YouTube, Voodoo, Amazon, and so on. And we can look into particular services like Netflix, for example. This is just showing Netflix traffic. In this case, the average bit rate goes a little bit more up and down, but that doesn't matter. Okay. We have other things we need to look at if we maintain our network. There could be some kind of network congestion because something changed that's not under our control. This is the amount of traffic for a particular customer from Dropbox. And it's looking into this traffic by peer. So what Dropbox did during 2015 is they went away from Amazon, and they are now using their own CDN, their own data centers, their own boxes, and their own AS. So we are looking at Dropbox traffic, and we are comparing it to peers. And we see that for these customers, the entire traffic that was on their Internet 2 peering is now on their most expensive AT&T peering, because all the traffic didn't go away. It went a little bit up over time, of course. But everything that was yellow is now green, right? Or green or blue. So the entire traffic shifted because the new Dropbox AS is reachable primarily via AT&T. So changes anywhere out on the network can have more or less bad influence on your over-the-top traffic services as well, because it might utilize a link that's mainly there for receiving video traffic. Another thing I briefly talked about already is understanding the service supply chain or cyber supply chain. And this is an example for a service like Instagram, for example. So what is all necessary to have this Instagram service working? Or this Instagram service has different dependencies, we could say as well. So it depends on Akamai, and it depends on Amazon, storage, and EC2 as well, and it depends on Facebook for mainly for login. Yeah. Instagram became part of Facebook, and you get an understanding of, okay, if some of these services fails, or if some of this here fails, that might be compensated. So if you see, okay, these all go to akamai.net, so one of those might fail, that might be okay. These others have only single lines mounted, so a failure there would definitely have an impact on the service like Instagram. We can do the same for video service providers as well. It's just an example. Our Cloud Genome feed and logic engine is basically doing it's scanning the internet, building something like a catalog, mainly like comparable to what Google does. Is they are indexing websites, we are indexing IP addresses, and map it to the according service. So we know which IP addresses is Netflix using for delivering streaming traffic, for example. And knowing that allows us to compare and combine, correlate these data, and show you exactly what is Netflix traffic. And that works even better if these services are encrypted, because the only thing you need to do is you need to connect to it, you get the certificate, analyze it, and you know, okay, this is Netflix streaming server in Boston or wherever. So it's it's mapping the internet and building these cyber supply chains. So there are a series of use cases we could think about. I guess if you get this presentation, you could go through it later, but you can answer questions like how much YouTube traffic is on this Verizon transit link consumed by premium enterprise customers somewhere in the network. Or how much HBO Go traffic is Akamai delivering from this router to 6 megabit DSL customers, for example. Other things which are more about quality of experience is what is the ABR of Netflix streams consumed by premium cable users in Boston on this level 3 transit link. So you can correlate all this information and you can figure out what's a good and what's a bad peering partner. So sometimes for some customers it happens that they increase their transit capacity or their peering capacity to a certain service provider, but their quality doesn't go up. So for transit that means, okay, I can add as much capacity as I want, the quality will never change because there might be a problem outside of my network, or very likely there is a problem outside of my network, not under my control. So how does this basically work? Our solution is a big data platform, and we consume data from different kind of data sources. So we consume generic telemetry information. This is really needed. So NetFlow information, everything starts with NetFlow information. Then we add SNMP information to know capacity on links, interface description, these kind of things. And then BGP information to understand traffic paths through the network, where's traffic coming from, going to, and so on. We also support modern types of streaming telemetry, like protobuf, gRPC, YANG protocol data. We can do netconf and other, like OSS, BSS. So any data that is valuable for your use cases could be used and imported into our systems, or we can connect to a different database. That's why we call it connectors. On the other hand, we provide all the information in our database to other systems to do things with it, right? Mainly for example, for our UI. So our UI is, of course, connected to the database to start queries. And we can do flow spec or open flow and feed information via this log to other network management systems. So all this information comes into the system and is enhancing the information we already have. So everything starts with a NetFlow record. We add then SNMP information to get an idea about where did the traffic enter the network, which interface and which router. Add then BGP information, and another term we have is DNS flow. DNS flow is a deep field open source project. It converts DNS responses into something like a flow record to be used by the deep field platform to get more information about what's going on here. The next part is our cloud genome feed information, so the mapping of services to IP addresses, because NetFlow just has information about IP addresses. We need to add more information to get the right context about this flow. And finally, you can add your data. So at the end, you will have a very rich data set in the database where you can do any queries against to figure out what's going on. All this is then stored in a multi-dimensional database. So multi-dimensional means it's not just tables, so you can correlate, combine everything in your queries you like. That's not the entire thing that needs to be done, because now you have a huge set of data, but you need some logic to do something with this data and to turn this into actionable information for you. So to calculate the average bit rate per stream, for example. That's something that's the real-time streaming logic engine is doing. We can do alerting, for example, as well. So that's really huge different from DPI solutions, because they may be able to show you the average bit rate as well, but normally they cannot alert you if something goes wrong. So what we do is we could baseline the service, and if, let's say, the average bit rate drops down from 3.5 megabits to 1.5 megabits, we know, okay, there's a problem in this region. So this covers your entire network. That's the idea behind. So these logic engines are used in different points in the network and are useful or responsible for different reportings. The best way to watch or to understand this is where is it done. So performance, for example, is measured per stream performance on CMTSs, on DSLAMs, on your fiber to the home, or on Wi-Fi connections. So you know exactly where in the edge, in the access part of your network is a problem. If one CMTS is delivering a bad performance, or is it everything? Why is it? Do I need to split this CMTS into two nodes because they are overutilized, or is it still okay? So this is the performance logic engine. Topology map is more or less looking into how is the traffic traversing your network, how is it delivered to your different regions, and is it traffic that's coming from the outside of the network, or is it traffic that has already been in your network on caches, on CDN caches, or are these your own apps, your own TV services, for example, so you can monitor those as well. And then we have the service map to understand traffic that's where you may not have the entire knowledge about because it's outside of your network, like what is Netflix traffic, YouTube traffic, where are these services, where are they hosted, are they delivered from a CDN, is my transit provider caching them, or do I get them directly via a peering, for example. So it helps to figure out that there might be a problem or not, and where this problem is, and how to quantify it. Questions? Yes?
Do we correctly understand that your solution is agnostic in regards of ciphering or not ciphered connection? It works even on HTTPS streams.
Yes, indeed.
Is that correct?
Yes, indeed. So, as a comparison, we can tell you that someone is watching a stream, that there is a stream and the performance of the stream, but we cannot tell you which kind of movie it is. We cannot tell you anything about the content, just that there is a stream and the performance of the streams. But that's normally enough for most network operators.
And just by curiosity, what is the rationale behind the fact that Netflix is ciphering the SD streams? Why do they do that?
Why they do that? So I'm not 100% sure, but there is this kind of story about it. I guess it was a DPI vendor who made a press announcement and said, okay, the new series, whatever, House of Cards or don't know, has been watched by so many users. And that's knowledge that Netflix want to have for, that they don't want to share this information with their competitors and so on. So they said, okay, we want to prevent these kind of vendors to know what we are delivering. Yeah. Yes?
Thanks. Paolo Lucente. I had a question on your slide 22. So you were mentioning generic telemetry, streaming telemetry, and things like that. So you started elaborating on what you do with the generic telemetry. I was curious, what are you using streaming telemetry for nowadays?
Yeah, indeed. So with that, there are going to be problems with generic telemetry because it doesn't scale anymore. There is one large company, Google, which said, okay, by the end of 2016, there will be no SNMP anymore in our network, right? So, but there need to be an alternative for SNMP. So the usage of streaming telemetry is, for example, to introduce the router to send us a particular data set regularly, as an alternative to, let's say, SNMP, for example, because SNMP is polling and streaming telemetry is just streaming out information into our platform. But to be honest, there are not many customers using it. That's Yes.
That was my question. Google is always optimistic, and we share their optimism. And also on the vendor side, I was wondering. I mean, I didn't see. I play a little bit with streaming telemetry myself, and I don't see much going on. Like you have maybe interface counters or segment routing statistics, things like that. But yeah, I was wondering actually if that is future looking, or you are already doing something with that.
Yeah, but you're right. So everyone is asking for it, right? We are doing a lot of RFIs, RFQs, and these kind of things. Everyone wants to. Do you support streaming telemetry? Yang, NetConf, yeah.
I was wondering about the, Elisa, I was wondering about the other that you mentioned. So how would you, because for every piece of data you add, you would have to merge it with the existing data set somehow, or at least know how it kind of fits together. So if you want to add custom data to it somehow, you would have to come up with like a rule set that it, I don't know, based on whatever keys you want to merge it or something like that? Yeah, so the key information for all additional data sets is something like an IP address or a prefix that allows us to correlate it to other data sets. But yeah, indeed. But it could be anything.
It could be basically anything, yeah. Some customers use, the main use case is for distinguishing between different kinds of customers. Who is connected with DSL, cable, mobile, DSL up to 6 megabits, 16 VDSL. So to know, okay, the idea is if a customer has more bandwidth available, do they use it, right? So is there a change if I provide VDSL everywhere, or if I upgrade everyone from 6 megabits to 16 megabits for free? How does the traffic change in my network? And most of them, it's dramatically changing. Yeah, more bandwidth available is used.
That's good, because anything you have like in your local customer database, whatever business logic you have stored somewhere else, you can map on top of that.
Indeed, could be security information as well.
Maybe you already told about it, but with Netflix, you're looking at the actual bitrate transmitted, HTTPS or HTTP, but are you also looking at the manifest file that goes around with it?
No.
Not yet. It's probably going to be interesting in near future.
Yes.